Complex ion equilibria. Transition metal ions are often good Lewis acids. Remember, we talked about 3 different types of acids. Lewis acids were referring to what the electrons are doing. And if you think about a Lewis dot structure, right, what do the dots represent? The electrons, right? So the Lewis acids are the ones that are talking about the electrons. So an acid is an electron acceptor. A base is an electron donor. So, well, how do we remember that? H plus is an acid, yes? Does it have any electrons to donate to anybody? It has no electrons at all, right? But if we get it with hydroxide, the hydrogen ion and the hydroxide ion will react. The oxygen here has lone pairs. It's donating those lone pairs of electrons to the hydrogen. The electron donor is the base. The electron acceptor is the acid. So water molecules can act as Lewis acids or bases. They can act as bases to hydrate transition metal ions. So if we have a solution containing silver ions, those silver ions are actually hydrated. Silver ions do not really exist as bare ions in water. Just like we talked about, hydrogen ions don't actually exist in water, right? We can write them like this, but we understand that they're actually connected to a water molecule and making hydronium ion. It's just convenient to leave the water out and just we all understand that it's there. So these ions are often hydrated. So here we have silver, and it's got 2 water molecules associated with it. The silver ion has empty orbitals. The water has lone pairs on the oxygen, and so the oxygen donates electrons to the silver and makes bonds and makes this complex ion. How do we know that there's 2 waters on each silver? I don't know that off the top of my head, and it actually doesn't end up being important. This is just an example, okay? So a complex ion, this is a complex ion, is one where you have a central metal ion that's bound to 1 or more ligands, and that might be a new word, ligands. A ligand is a neutral molecule or an ion that acts as a Lewis base with a central metal ion. So here, the water molecules are acting as Lewis bases to the silver ion, and it forms a complex ion. I realized yesterday as I was lecturing about this that I should probably change part of the schedule, and I think in the future I'll do experiment 26A after this section, because at least we've introduced what complex ions are, and I think that might make experiment 26 make more sense, but I did not do that this semester. So you've got that hydrated silver ion. If a stronger Lewis base is in the solution, it will displace the water. So here we have the water being a Lewis base to the silver. And if we bring in ammonia, ammonia is a weak base, but it's a stronger base than water, right? And so this one is like, no, I'm stronger, I'm better, I'm donating my electrons to the silver. Get out of the way, water. It's a stronger base. It's going to push the weaker base out of the way. And so we end up with AgNH32+. Because this ligand is neutral, the charge on the complex ion is the same as the charge on that transition metal ion. And the 2 water molecules just displace. So for simplicity, we'll often just leave the water out of the equation, like we often do with hydronium ion. We just call it H+. So here, silver ion plus ammonia makes this complex ion. Well, was the silver ion ever actually alone? No, some water molecules were helping it out, but now the base came in and displaced them. It's just much simpler to leave the water out. So this is the chemical equation for the formation of a complex ion. This is an equilibrium, and so we can have an equilibrium constant. So here's yet another K to add to the list, Kf. Kf, the formation constant. And this is calculated the way all the other equilibrium constants were. You take the products and divide by the reactants. If anything has a coefficient, that is the exponent on the concentration. Okay? So we're doing some stuff that's a little different here, but it's just a variation of things that we've already learned. Here's a list of formation constants. There's a more extensive list in the appendix of your textbook. These are not something that anybody memorizes. If you need them, they'll either be given in the problem or you can look them up. How do you know what sort of a complex ion something will form? How do we know it's AgNH3 Well, if we see that we're going to have a complex ion between silver and ammonia, what we do is we go to the list of formation constants and see what the options are, right? So they're telling us there's AgNH3 There's no other ones listed here because this is the one that forms. Do we need to understand why it's this one? No, we don't. It's just like, oh, well, that's the one, and so here's my formation constant, okay? Okay, let's do a problem here. You mix a 125 milliliter sample of a solution that is 0.0117 molar in nickel chloride with a 175 milliliter sample of a solution that's 0.250 molar in ammonia. After the solution reaches equilibrium, what concentration of nickel ions remain? We're given the formation constant for NiNH3 Okay, so what's going on here? How do we approach this? We can actually approach this in the same way that we approach a calculation in a titration. So if we have a weak acid in solution and we're titrating it with sodium hydroxide, what did we do? We looked at the millimoles of hydroxide present and the millimoles of acid present, and we did the stoichiometry table, moles initial, change, and moles after. And we figured out how they reacted, and then we took those moles and converted them back into molarity, and we made an ice table. And so that's what we're going to do with precipitation problems, complex ion problems. Okay, so what do we have going on here? Well, we have nickel chloride in solution, right? Does the chloride do anything? No, it doesn't. So this is a soluble ionic compound, and so it's going to separate into ions. And this is something that hopefully, if not already, very soon, you'll just be able to kind of understand. Okay, I've got a solution of nickel chloride. That means I have nickel ions and chloride ions, right? So we don't care about the chloride ions. We're just looking at the nickel ions. So we have nickel ions and ammonia, right? So nickel ions plus ammonia form a complex ion. Well, what complex ion do they form? Well, it's the one they gave us the Kf for. So this is NiNH3 2+. Is that a balanced equation? No. And these are generally pretty simple to balance. We have 6 ammonias over here, so we just need to put a 6 over there. Okay? So I'm wishing that I had written that down here. So I'm just going to copy it down there. Ta-da! So we need to look at moles of initial, change, and moles after the change. We're going to assume that this reaction goes to completion, and then we'll look at the equilibrium after that. And this is a very reasonable thing because this equilibrium constant is very large, 10 to the 8. So we have to figure out what amounts in moles or millimoles we have of each of these things, right? So I'm going to write this out, but I'll probably have to erase it to make room. That's not what I wanted to do. We have 125 milliliters of the nickel chloride. We're given the concentration in moles per liter. Right? Remember, that's what capital M means, moles per liter. Well, I can put milli in the numerator and the denominator of that and make it millimoles per milliliter. And we've talked about this, but it takes a little while for it to sink in. So to find the millimoles, I just take the milliliters and multiply by the molarity. This is not something you have to write out all the time. If it helps you to write it out, then absolutely do that. So 1.4625 millimoles. So 1.4625, and that's millimoles. There's not really much space there. How many millimoles of ammonia do we have? We take the volume times the concentration, right? So 175 times 0.25, and that says 43.75. There's room there, so I'll write millimoles. That seems like a big number, huh? It's okay. How much of the complex ion is present initially? 0. So this is my stoichiometry table. I'm looking at amounts in moles or millimoles, and I'm going to assume complete reaction. So because I have this coefficient of 6, this is a little more complicated than for an acid-base reaction where it's all going to be 1 to 1. So if I look at these, I'm trying to figure out, well, which one is going to get used up? I need 6 times as much of the ammonia as I have of the nickel, but 43 is definitely more than 6 times 1.4625, right? So I can be pretty sure that this is my limiting reactant. So that's going to lose 1.4625 millimoles. And how much ammonia am I going to lose? The same amount times 6. Because of this coefficient. How much of the complex ion am I going to form? Plus 1.4265. I mean, yeah, 460. I can't write and talk at the same time. So we're going to end up with one of these being 0. We'll do the easy math first. And then this one, I have to use a calculator for that one. So 43 minus 6 times 1.4625. 34.975. Everybody okay? Now I want to make an ice table, but I need concentrations. So how do I make millimoles into molarity? Divide by milliliters. So for the NH3, the concentration at the end of my stoichiometry table is going to be 34.975. These are going to be the initial concentrations in my ice table, divided by the volume. We added two solutions together. We had 125 milliliters plus 175 milliliters. Right? So we're taking this solution and we're mixing it with that one. So we have a new volume. Again, this is like what we did with pH calculations. So I've got 34.975 divided by the quantity 175 plus 125. So we took our millimoles, we divided by the new total volume, and we get this concentration. That's for the ammonia. How do we find the complex ion concentration? Same way. We're just going to take this number, its millimoles, and divide by the same volume. So that's going to be just so complex ion is going to be 1.4625 millimoles divided by the total volume. Zero point 004875. So we looked at the chemical equation for the formation of this complex ion. We know which complex ion forms because we are either given KF or we go look it up. If you go look it up in a table, this is willing to bet a fair amount of money that this is the only complex ion you'll see between nickel and ammonia. So it's not a big mystery, but I don't expect you to know that formula. We make a stoichiometry table. We start with the amount of millimoles of each thing that we have. We look at the change. At the end, one of our reactants is going to be 0. And then we take these millimoles and we find the concentrations. And now we're going to use those in an ice table. So here, we're going to make our ice table. And we've got nickel 2 plus, and we've got 6 NH3, and we've got our complex ion. I don't know why I felt like drawing lines this time. What's the initial concentration of nickel ion? It's 0. We go back to our stoichiometry table. 0 divided by whatever the volume is still 0. So this is 0. And the initial concentration of ammonia is this 0.1166 that we calculated. And what is the initial concentration of our complex ion? It's this concentration that we calculated, right? There's a lot of numbers here, there's a lot of steps, right? And so I really want you to see where all of these things are coming from so that you can do problems like this yourself. Okay, initial concentrations. And then we look at the change. Right. So the change we're going to represent with X. This one is 0, can't go lower. So when we did the stoichiometry, we pushed everything to the product side. And that makes a lot of sense because we've got this high equilibrium constant. And now we're going to look at the small amount that comes back. So this is going to be plus X. And the ammonia is going to be what? Plus 6X. And the complex ion is minus X. This is chapter 18. Now, equilibrium constant expression, right? So Kf is equal to the complex ion, that's the product, divided by the reactants, nickel and ammonia. And what's the exponent on the ammonia concentration? 6. Wow, it's a lot. It is a lot, but that's what it is. And that's one of those things that's really easy to overlook, and then the answer's like really wrong. I'm going to get rid of this because it's in the way. So now we're going to take our Kf, 2.0 times 10 to the 8th, and I'm going to plug in the things from my ice table. So the nickel here is 0.004875 minus X, and the nickel is X, and the ammonia is 0.1166 plus 6X to the 6th power. You can use your solver to solve this one. What we found yesterday was that the calculator complained a little bit about the starting value that we gave it. So we got a couple of sign change errors and a couple of max iterations when we tried different things. And so we just had to keep trying different numbers until we got the right one. This is a situation where it's probably easier to just use X is small. But if you don't like X is small, you can definitely use the solver on your calculator. So X is small means that where I'm subtracting X, it's so small it doesn't matter. Even if I'm adding 6 X's, it doesn't really matter. If I throw 6 peaches onto the big truck of peaches, does it matter? No, because there's thousands of peaches in there. It just doesn't matter at all. So then I have to solve this problem. Now, this is going to be easier for your solver to handle, right? So again, algebra not your thing, type this into your solver. Anybody get a solver answer yet? What was it? You're given an error? Okay. Okay, so she got 9.675 times 10 to the negative 6. So if it's giving you an error, double check that you entered the equation correctly. Did you start with x equals 0 the first time? Kyla, what did you start with? Okay, you've got a different kind of calculator. Yeah.
I just had a question.
Mm-hmm.
For the bottom when we're solving for KF, where does the x in front of the parentheses come from? If we're already adding the 6x.
That's a great question. So we've got our ice table here, right? X is the concentration of nickel. So in the denominator here, we have nickel times this quantity to the 6th power. So that's where this x comes from. Yeah, good question. Is it still giving you an error? Oh, she's trying it for you. So usually with the TI-36X Pro, starting with x equals 0 works. If that doesn't work, I'd try 1 or -1. On this example, we know that x should be a small number, right? And so you might try 0.000, maybe pick your number of zeros, 1. Try just a really small number. That's what worked yesterday. So the problem is asking us about the amount of nickel that remains in solution. And so that is x. And so our nickel concentration probably be reasonable to maybe do 2 sig figs, 9.7 times 10 to the minus 6 molar. Yeah. Why did I cross out the x's? Okay, that's a good question. So I crossed out both of these. Whatever you're adding or subtracting, it doesn't matter what the coefficient is. I mean, if this was even 500 times x, which you'd never ever see, it's still going to be small relative to the number it's added or subtracted from. So, I use the analogy of a semi-truck full of peaches at the weigh station, right? And if you throw one more peach on there, does that change the mass that the scale shows you? No, it doesn't. Well, but if you throw 6 peaches on, is that going to have an effect? No. Even if you throw 100 peaches on, it's probably not going to make a difference because you have thousands, right? Because what you're adding it to is so small. And so the x is small approximation. Any x's that are added or subtracted, you're going to get rid of. This one is just by itself. Or if we had 6 times x here or something, that would stay. We can't get rid of all the x's because then we have nothing left. Any other questions?
Could you check for x is small, please?
Yeah, I can check for x is small. So we should always do that. So here I've got my x value, and I'm going to divide by the smallest thing it's being added or subtracted to make the percentage be as large as possible. So this is the smallest, so I'm going to just divide by this, divide by 0.004875, and multiply by 100, and I'm getting 0.2%. So that's well under 5. Any other questions? These are great questions. Everybody get the solver to cooperate that wanted to get the solver to cooperate? So the book gives 9.6. Does that matter? We had 9.7? Not really, no. What I suspect happened is I probably carried more digits through the calculation than they did when they did the book. So complex ion formation has a big effect on the solubility of those ions. So I'm going to read this, but it's got so many words in it, it doesn't really make a lot of sense. The solubility of an ionic compound containing a metal cation that forms complex ions increases in the presence of Lewis bases that complex with the cation. What? So if you have a cation that forms a complex ion, it's forming that complex ion with a ligand, something, right? Ammonia or water or something. If you add a bunch of that ligand to your solution, the solubility will go way up. That's what it's saying. The most common Lewis bases that are going to increase solubility are ammonia, cyanide, and hydroxide. So here we're looking at a solution of silver chloride. Silver chloride is not very soluble at all. So most of the silver chloride is just sitting down here as a solid. There's just a teeny tiny bit in solution here. Adding ammonia to this. So ammonia is going to complex the silver ion and form a complex ion. And what we see is that now all of the silver chloride dissolves. So what happens there, the addition of the ammonia changes the equilibrium constant by a factor of 17 million. That's big. You multiply something by 17 million, it's really big. So silver chloride that is almost insoluble now becomes actually quite soluble. So let's look at how that happens. So here we have the equilibrium for silver chloride dissolving in water. And KSP, the solubility product constant, is very small, 10 to the minus 10. Here we have the equation for silver and ammonia forming this complex ion. The formation constant is large. It's 10 to the 7. And so what we can do is we can add these two equations together. When we do that, what happens? Well, here silver is being formed, and then as silver is formed, it gets complexed with the ammonia. So when we add these two together, the bare silver ion cancels out, and we end up with silver chloride plus ammonia gives us the complex ion plus chloride. Are you okay with that? These are two steps that are happening. It's much easier to look at after both of them have happened. When we add two chemical equations, what do we do with equilibrium constants? We multiply. With delta H we added, but this one we multiply. So KSP times KF gives us our equilibrium constant for this equilibrium, 3 times 10 to the minus 3. So this is still a small number, but it is much bigger than 10 to the minus 10. Any questions? So which compound, when added to water, is most likely to increase the solubility of copper sulfide? Sodium chloride, potassium nitrate, sodium cyanide, magnesium bromide. Where does this come from, right? Well, how could adding something increase the solubility of something else if it forms a complex ion, right? Well, how do we know if these form complex ions? Well, we're going to go back here to where it said the most common Lewis bases that increase solubility are these guys. Do I expect you to remember those three on an exam? No, I don't. So cyanide is one of those that increases solubility by forming complex ions. The other ones, chloride, nitrate, bromide, are not on that list. So it's the sodium cyanide that is likely to increase the solubility. Any questions? If you didn't have access to that, short list there, what you could do is you could look for complex ion between copper and chloride, copper and nitrate, copper and cyanide, copper and bromide in a KF table, and you're only going to find one for cyanide. A lot of metal hydroxides are not very soluble. Ones that are the alkali metals, sodium hydroxide, potassium hydroxide, those guys. The alkaline earth hydroxides are slightly soluble, like calcium hydroxide, but other things like aluminum hydroxide are pretty much insoluble in pure water. These metal hydroxides, though, are more soluble in acidic solutions. So how does this work? Well, some of these metal hydroxides are amphoteric. They can act as acids. And so because they can act as acids, their solubility will be increased in a basic solution. So if we take our insoluble aluminum hydroxide and we put base in it, we can form AlOH4 minus. This one is neutral, and based on that, I would predict it's not soluble. This one has a charge. This is a complex ion, is most likely going to be soluble. So what we find for aluminum hydroxide is that it's soluble at high pHs and at low pHs, but insoluble in pH neutral. So I'm going to explain all of this to you. I do not expect you to be able to explain it back to me or anyone else. My goal in explaining it to you is that you'll follow enough that you believe me. You might say, oh, no, I'll just believe you, please. Please don't tell me about it. And I'm going to tell you about it anyway. This is like, maybe some political thing, right? And someone explained it to you, and you're like, oh, okay, I see how that is. But then you go try to tell your sister about it, and you say, well, this is this thing. And she's like, I don't get it. Explain it to me. And you're like, I heard a great explanation, but I can't spit it back to you because I don't know it that well. But you are convinced because you heard the explanation and you believed it at the time. That's what we're going for here. So consider a hydrated aluminum ion. Remember, aluminum ions are acidic. The small, highly charged metals, Fe3+, Al3+. So here we have aluminum, and it's going to be a complex ion with the water. Because just like the silver ion, you don't actually have Al3+ ion alone. It's going to be complexed with water molecules as the ligands. So if we have water here, this can act as an acid, right? Donating a hydrogen to the water molecule to make H3O+. And when it does that, one of these 6 water molecules has lost a hydrogen ion. So now we have 5 water molecules and 1 hydrogen ion. And the charge on this then changes from 3+ to 2+ because this is a minus. If we add base to this equilibrium, the base is going to react with the hydronium ion. If we are removing the hydronium ion by chewing it up with added base, what does that do to this equilibrium? Does it drive it to the right or to the left if we're removing this product? It'll go to the right. It's like, you took my hydronium ion. Well, I'll show you. I'm going to go back over there and replace it, right? Just equilibria are really ornery that way. So adding hydroxide is going to reduce this, causing this to go to the right. And so here, another hydroxide in there. Essentially what we're doing is we're taking another hydrogen ion off one of the waters. And so now we have H2O4, OH2. And another hydroxide, now we've got H2O4, OH2, losing another one, we get H2O3, OH3. This is neutral in charge. If we get rid of the water molecules in that. That's the same as OH3, aluminum OH3, aluminum hydroxide. And that's going to be insoluble. If we add more base, so we've got our insoluble thing here, and we add more hydroxide. Well, there's still three water molecules here, and one of those can donate a hydrogen to the OH minus. And this is a typo that I just discovered yesterday. So the H2O goes from 3 to 2. The OH3 is supposed to go from 3 to 4, not 2. And now we've got an ion again, and that's going to be soluble. So at low pH, the aluminum is soluble, and as we get to more neutral pH, it's not soluble, and then if we become more basic, it becomes soluble again. Is that weird? It's weird. There are several that do this. Aluminum is the only one that I would expect you to remember. So aluminum hydroxide is amphoteric. Aluminum hydroxide is soluble at low pH and at high pH and insoluble at neutral pH. There will probably be one question on the exam about that. So if you're struggling with other things, I give you permission to just not pay attention to that. So this is showing in pictures. So here at low pH, we have this complex ion form with the water. And when we get to pH neutral, now we've removed hydrogen ions from 3 of these guys, and so we form this aluminum hydroxide neutral compound, which is insoluble. And then as we add more hydroxide, then we take off another hydrogen from the water, and we again form an ion that's soluble. So you asked, is aluminum the only one? No. Chromium, zinc, lead, and tin also do this. The only one that I expect you to remember is aluminum. So the extent to which it will dissolve in both acid and base depends on how amphoteric it is. If it's very amphoteric, it will be soluble in both acid and base. If it's not very much, then it won't be as soluble.